All right, thank you very much for having me to give a talk at this conference again. I'm sorry I have to do it via Zoom again, but it's just a little hard to travel right now with my teaching load. But thank you for letting me give my talk via Zoom. So today I'm going to talk about some joint work with Anton Nazarov and Olga Postnova. And this is maybe a little bit different than kind of the main focus of this conference, but we're going to look at this study of long-term behavior of random partitions of a certain measure coming from representation theory. And we're going to talk, at least at the beginning, about a general technique due to Okunkov and Reshetikin that is motivated from the boson-fermion correspondence to study these limit shapes, which that is based upon forthcoming work with Anton Nazarov, Pavel Nikitin, and Daniil. I always have trouble with his last name, so I'll just show you where it is later. And then we're going to move into some more general case. And from there, we're going to go into some combinatorics where we're going to use stuff basically associated with the quantum groups of Lie algebras. And then through Cauchy crystal bases to develop formulas that we're going to be able to prove a few other results. So let's get into what classical skew Howe duality is this, I want to take this representation where I have the general linear group GLN, and everything I'm going to work on today is going to be over C. So all my representations are complex, GLN's complex. And then I can take GLN cross GLK, it's a perfectly good Lie group, and look at its natural representation. So I have a Vn, which is just n-dimensional space, and Vk, k-dimensional space, where you just naturally have matrices. And GLN acts on the left factor, GLK acts on the right factor. And so I can build that representation as a tensor product of the two. And then I take its exterior algebra. And there's a natural way to build a representation of GLN cross GLK on this. And this is still a semi-simple Lie group. So I can decompose it into a direct sum of simple modules, which look of this form: V lambda tensor V lambda prime, where the V lambda is for the GN and the lambda prime is for the GK. And the fact that it's indexed by the same partition lambda that's contained inside of an n by k rectangle is precisely the statement of skew Howe duality. And so that's some representation theory. And then we take characters. And what this basically amounts to is each irreducible representation goes to a Schur function. And coming from the exterior algebra side, you get this, you get a nice product formula where the number of variables here are I is going to go to n and j is going to go to k, not to infinity. Oh, sorry, no. Well, essentially, we will restrict it down to finitely many variables, but this actually holds for infinitely many variables. If I just make n and k, well, I guess since I want to do it for GLN and GLK, I'll restrict myself to finitely many variables. And over here, I have xn and yk. So I have x1 up to xn and y1 up to yk for these Schur functions. And again, because I'm fitting my partition inside of an n by k rectangle. I have my partition here, and this prime means I take the conjugate shape. So I essentially am reflecting it over this line here. For reference later on, I'm going to need this bar, this complement shape inside of the n by k rectangle. And then if I take the dual Cauchy identity and just divide by this product formula and take any particular partition lambda, then basically I take one term in the sum, I get a measure on partitions. And I know it's and it's not only just a measure, but it's a probability measure, because everything on the right-hand side, assuming like my x's and my y's are positive, then the right-hand side is positive and it sums together to equal 1. So essentially I can take random partitions now with this probability of getting the partition lambda. And some particular examples is when x is equal to 1 and y is equal to 1. What it turns out is that this ends up being equivalent to a certain random point process where you choose points in this case, discrete space with finite probability. And the way you do this is by determinants given by Kraft-Schuch polynomials. And for this case, essentially, we understand something about the limit shapes and the boundary fluctuations, but we're going to basically talk about the limit shape and give a proof of this that we're going to more or less kind of prove it 2 ways today. And then we'll talk a little bit about how to get the boundary fluctuations. But another case that's been studied is when x is equal to 1 and all of the y's are equal to alpha, a fixed constant alpha. This is this process known as oriented digital boiling. If you study how the longest longest row of the partition is fluctuating. This was done by Grosvenor Tracy Whittam in 2001. So if we want to actually to work with this, one of the techniques that we use is using free fermions and building a determinantal point process due to a technique of Okunkov and Reshetikhin. So how I think about this is I take a partition lambda and I write it in Russian notation. So I get to write my partitions like playing a big game of Tetris, and I stack and everything falls in to the corner here as much as possible. And my first row is measured here. My second row is measured here, etc. And when I draw the partition this way, well, if I put the corner precisely at 0, then the down steps, if I put a particle in the middle of them and project it down, lie on half integers. And that gives me this way of translating the positions of the particles into a partition, and provided that only finitely many particles have moved from their initial position, which is the ith particles at position I minus a half. And so from this, we think of elements in this space as being semi-infinite wedges, where we just put their position as the index of some basis vector in some copy of C infinity, where here I'm being a little loose with my notation to what maybe a measure theorist would like, but I'm really thinking of this as the direct sum of these vi plus a halves for I being an integer. And then I take its exterior algebra and then just look at these semi-infinite wedges. And because each index can only appear once because it's a wedge product. That corresponds to the fact that I can only have one particle at each half integer, at most one particle at each half integer. And this space is known as fermionic Fock space in a lot of circles. Maybe the physicists will get upset about that because I should put an A instead of a the in front of it. But kind of in this boson-fermion correspondence, there's just one fermionic Fock space. And so I'll write my basis vectors as being partitions. And for this, I'm just, for those who are experts, I'm restricting myself to charge 0. So I'm not, I can have an extra shift in there, but I'm just always going to say my particles always start to the left of 0. So this is a basis for this space. And we can actually give this space a Clifford algebra action where we have an operator psi that creates a particle at I and a psi I star that annihilates a particle at site I. And of course, if we can't do this, say a particle is already at site I and we apply psi I, then we say the result is 0. So essentially what we're doing is psi I is just vi wedge, the vector that we started with. And then it turns out that these operations satisfy these relations here. And, this would allow us to, potentially we would move out of our original Fock space, but I'm going to restrict myself to these current operators, where how you want to think about them is when I apply a current operator to basis vector V, then it moves a particle else. If I apply AL, then it moves a particle A steps to the left if it's in all possible ways. And so I'll get a linear combination, but I still get something back in my fermionic Fock space. And with a little bit of work, you can show that these satisfy the relations of an infinite dimensional Heisenberg-Lie algebra. Basically, what that means, the bracket is 0 unless m plus L sums together to be 0, in which case you get a coefficient of m in front. And there's a nice anti-involution that sends psi I to psi I star and vice versa. And what this does is it sends AI, the current operator AI to A minus I. This star allows us to construct a dual space where we have dual vectors by just taking the stars of everything. And this is a dual space in the sense, well, there's going to be a natural pairing. And this pairing is given by the fact that these basis vectors are orthonormal. And it turns out that this pairing is also extra nice because I can basically put any operator in the middle and I don't care about where I write the parentheses. It's completely unambiguous. And so basically I can write these, I have my basis, dual basis. I can write matrices by taking pairings of this form, of this form here with whatever element inside, and I can basically write it as a big matrix. And the fact that we have both this Clifford algebra action and the Heisenberg algebra action on the same space is essentially what's known as the boson-fermion correspondence. Now, we're going to take this and we're going to start building something called a half-vertex operator, where for the purposes of this talk, I'm going to have these PLs be the power sum symmetric functions. So it's just x1 to the L plus x2 to the L, dot, 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 up to however many variables we have. I'm going to divide by L and multiply by my current operator. And I'm going to sum over all current operators, say from 1 equals to infinity. That will be my gamma positive, and then my gamma negative will be when I sum over all of the negatives. And a very important fact of the boson-fermion correspondence is that if I stick in one of these half-vertex operators in between mu and lambda, I get the skew Schur function. In particular, if I take mu to be empty, I get the classical Schur function that we saw, we kind of hinted at before, and I can provide an explicit definition if anyone would like to hear it. Now, some properties of these half-vertex operators is that essentially if I have two sets of variables x and y, well, I can split that up into a product of two half-vertex operators with the same sign. And that just follows from the Baker-Campbell-Hausdorff formula, or you can explicitly expand out the exponential in the way that you would, write the Taylor series of e to the x. And because you're only dealing with, say, positive AIs, ALs, and the Heisenberg relations, say those commute with each other, therefore everything commutes and I can separate it out like this. The interesting relation is when gamma plus interacts with gamma minus. And these don't commute with each other anymore because that non-trivial Heisenberg relation. But when you go and you expand it out and are careful about stuff, what you find is you end up with a function that will look like this. And it comes from Baker-Campbell-Hausdorff with, you get the exponential of the log of this function. And so the exponential of the log cancels. So how do we do this? How can we use this for our problem? Well, we can derive things like the Cauchy identity as a first step by sticking in a gamma plus and a gamma minus. One way to do the computation is you commute them past each other and you pick up the extra factor of h. The gamma minus ends up getting absorbed into 0. The gamma plus gets absorbed into the 0, 0 being the empty partition. And so what you end up getting is precisely that Cauchy kernel here. But I can just stick in an identity map, an identity matrix in between, and then this is a Schur function, and this is a Schur function. And so I end up with the classic Cauchy identity. But we can actually go a little bit further, and there's an involution on symmetric functions that sends PL to -1 to the L minus 1 times PL. And I can then use this to build a new, just a slightly modified version of my vertex operator, my half-vertex operator, excuse me. And it's well known that this operation omega sends the Schur function S lambda to its conjugate. And so now I can play the same game as I did before. And I have gamma plus, but now with a gamma minus prime, I commute them past each other, or I stick in the identity element, and I end up, after all is said and done, because I have this relationship between the gamma prime and the gamma inverse, well, I can just rework everything to see that once I commute them past each other, I get this E kernel here, which is precisely the product formula for my skew Cauchy identity. So this is kind of a classical sort of picture now. And what we can do is we can define a formal, well, maybe I should call it a formal distribution, because I'm summing over all integers rather than positive integers. And I put a zj with a psi j in front and w minus j with a psi j star in front. And I have these two series like this. And with a little bit of additional work too, you can show that how gamma commutes with the series psi and psi star, you pick up these factors of these H kernels, these Cauchy kernels. Maybe it's inverse in this form. So Z is now a single variable. Here, this should actually be a W, because I have W here. And then, well, if I want to compute this value, I can apply the same idea as before, put in my power series, do the commutation, and reduce it down, which, I'll show you below in a second, but that's where we're going. The question now is, why do we want to do this? Well, if we look at psi I with psi I star, what we end up is a projection operator if there's a particle at site I. So if we apply this to any lambda, ket lambda, it is 0 unless there's a particle at site I, because it deletes a particle at site I and then adds it back in. If there is no such particle, then the psi I star would act by 0, and so the operator acts by 0. And so, as this says here, this formula is checking if there's a particle at site I. And why we want to do this is because if we want to check in the middle as we go do our Schur function, and then our Schur prime, our S lambda prime, is the particle at site I for that particular lambda. That's what we're trying to measure here. And, well, it turns out that if we then take a product of these and we want to understand if there's a particle at site I1 up to site IK, then, well, okay, this K doesn't have to depend upon the Schur, skew Howe K. It's unfortunate conflict of few variables, but we have this thing called Wick's theorem, which says that I can write this as this determinant here. And so my multiple point process is, if I want to measure the probability that there's a particle at site I, site I1, site I2, up to site IK, I have a determinant to do it. And it's all essentially the same function that only depends upon the site that I want to measure it at. And another small typo, there should be a star here. But, these two values are different. And so it's essentially just a small movement of the particle, not necessarily the same particle, but essentially it just all comes down to a function that depends upon these two indices and that only. So how do we actually write what this function is? Well, we use those generating series that I had before, and I just take their residues at the appropriate values. So if I do it generically k and k prime, then I'm just getting the residues, or because of W, this being in W inverse, this is all inverted, but it's essentially the same sort of residue type computation as before. And so I then use all of those commutation relations to move the gamma plus over here, the gamma minus prime over here, and that picks me up some factors, some in Z, some in W, and then I'm left with this expression here. And this expression you can actually explicitly evaluate, and what it becomes is a geometric series. And so because of that geometric series, I want to take the contour integrals to have the absolute value of W be less than the absolute value of Z in order for that geometric series to converge. And then these factors W, they just come from how I'm doing the commutation relations here. And then there's some extra conditions because of that with how the poles and the zeros behave with respect to the current, the contours, but it's not too hard to actually work out that the W contour has to contain all of the Y's and avoid all of the XJ inverses. And I think I also need a minus sign here as well. So that's what, now we have this integral representation, and we can apply certain techniques to actually study what the limit function is here, because the limit function, as I take n and k to infinity, gets concentrated on the diagonal, and there's a well-developed kind of well-developed technique for how to do this. However, what we're interested in is not just for GL, but other cases where we have skew Howe duality. And we have 4 such pairs. These are known as dual reductive pairs. And this gives us a measure and we can take characters and we can do the same sort of computation. But understanding this kind of half vertex operator picture is kind of lacking still. We don't know how to do it. At least I've never seen a way how to do that. So we're going to look at a simpler case. We're going to look at when we specialize all of those parameters to 1, or in other words, we're just going to take the dimension. And so our measure is, this is divided by 2 to the n times k. Our measure is essentially we take the dimension of these 2 representations. But now I don't want to just take the complements, the conjugate partition for the G2 group, the kind of right group action. I want to take the complement conjugate partition. It turns out this is what you want to get nice formulas, because you actually don't want B tensor or V n tensor VK, but it's dual. But some technical things aside, this is our formula. And if we want to get a product formula for this, just in terms of lambda, dealing with lambda prime is kind of a pain. So instead, what we do is we translate this problem into what happens when it's just G1. But we need to change our representation. and our representation then becomes a tensor product of a certain representation. And for the cases that we're going to consider, we have our type C, our type B, and our type D cases. Then basically for type C, we take the exterior, our representation V is going to become the exterior algebra of the natural representation. And for our types B and D, I'm going to take the spinor representation. Note that for type D, I'm taking O, not SO. And so if you want to describe this in terms of SO representations, I really want to take the lambda n with the lambda n minus 1, the direct sum of these two. So now we want to count the multiplicities. So in order to count the multiplicities, there's a very nice formula or a nice way to do it using combinatorial data, which is known as Cauchy crystals. So these representations here have nice description in terms of edge-weighted, directed, colored graphs where the structure of these graphs depends upon your Lie group that you're considering. Well, more specifically, it's given from its Lie algebra. You take the corresponding Drinfeld-Jimbo quantum group, you take the representation, and you take the Q to 0 limits of this representation. And that's what a crystal is, and it has a combinatorial description. But it turns out that you can actually translate this combinatorial description using this theory of Cauchy crystals into something that's a little bit easier to understand how to count the numbers of for these highest weight elements. And what it boils down to is a certain family of non-intersecting lattice paths. But these lattice paths aren't just in a square lattice, they're in essentially a triangular lattice. And in combinatorial circles, these are known as Dick paths. At least if they start on the diagonal and end on the diagonal. And in this case, that's what we're going to use. And all of these cases are going to essentially look like this, where we start our paths tucked into the corner here. Because of the non-intersecting condition, this corner is completely fixed. And then after some number of factors, which is depends upon our tensor power up here, we're going to end along some diagonal, and and those endpoints there is going to determine our partition lambda that we want. And so for types B and C, it really is just line in the triangle. However, for type D, because of that weird spinor representation being a direct sum, we have to add these extra second half edges here. So there's kind of a doubling along the diagonal, but this ends up being a natural thing from the kind of symmetry of the type D Dinkin diagram that swaps these two nodes. And so we can actually show one of our theorems. This is with Anton and Olga, as well as based with previous work with Sage and O, where we know that these multiplicities are given by these families of non-intersecting lattice paths. And since we have a family of non-intersecting lattice paths, there's this thing called the LGV lemma that I forget what it's called in physics, in math physics circles. I've seen it with a different name, but I don't remember what it is. But this Lindstrom-Gessel-Viennot lemma that says the number of non-intersecting lattice paths is given by a determinant. And it's given as a determinant from any point to any other point. And so I have then a nice determinant formula, but it turns out that I can even Q-deform this formula in a natural way. This natural description here comes from basically binomial coefficients or Catalan numbers, triangular Catalan numbers, but essentially it's binomial coefficients up to maybe some overall leading factor.
You have 5 minutes.
Yep, thank you. And you can Q-deform these, and what we're able to show is that these are equal to the Q character of the G2 representation we're after. And, well, we have these determinant formulas. We can actually evaluate them as a product formula. And from that product formula for these multiplicities, which is the same thing as our dimension here. And if we use the Weil character formula for the dimension of the G1 representation, we end up with a formula like this for our measure. And we get the square of a Vandermonde determinant, except with the variable squared that tell us the positions of our, that come from our lambda. And then we have some weight function, and that looks like a binomial coefficient as well, and some normalization constant. And in the case of GL-GL, this is precisely what gives us the Kretschuk measure. And if we want to compute the limit shape, well, we write things in exponential form with respect to some functional that depends upon the density of particles as we take our n to infinity. And we have some correction term that we have to deal with. But what we end up with is a Riemann-Hilbert type problem. And because what we want is the minimizer of this functional, which then tells us our limit shape. And we can show that this here is precisely the minimizer, which then means we now are able to give an explicit formula for our limit shape. And what this looks like is this kind of smooth curve here for the GL-GL. And all of the other cases are basically half of the GL case. And that's the general case, but this case of C equals 1 is actually very special because it now goes and ends precisely at the corner. This picture is slightly misleading. It doesn't go from the corner to corner. But yeah, the case C equals 1 is special. It's nice and flat. It's kind of degenerate. In general, the fluctuations around this corner behave like the GUE random matrix largest eigenvalue distribution, which is known as the Tracy-Witham distribution. But in this case here, well, it is related to something called the discrete Hermite kernel, where you get a probability measure using Hermite polynomials, and you only get kind of finite sort of little fluctuations that because the partition's basically trapped into the corner. And in general, if you start looking at this more general parameterization where I allow these more general parameters for the GL-GL, we're actually able to show that we get fluctuations that are given by the discrete Hermite kernel, and in the C equals 1 case, I take S equals 0. And what we believe is that this will actually hold for all of these other if we take more arbitrary parameters for these other skew-Howe type duality measures. But at this point, we're unable to prove it. But we're hoping that the boson-fermion correspondence will be able to give us answers. So thank you very much for your attention.
Thank you very much. So this talk is now open for comments or questions. Yes, Marek.
Yeah, so my question is related to the your presentation of weak formula for Bose-Fermi case. And in your case, it's only determinant, but this is for Fermi. But for Bose should be permanent. I am wrong, or there is some trick in your formula, in weak formula?
Yeah, so for Wick's formula, yes, we get determinants. I didn't quite hear the rest of your question. Sorry.
Maybe you
it's hard to hear.
Where weak formula where is only you determinant.
Yeah.
But for Bose case, that should be permanent, yeah. But here is determinant. The weak theorem should be replaced determinant in the. Oh, this is only for Fermi particles.
Right.
Or maybe there is some trick in your language, your presentation. Determinant you can change to permanent or not. This is just only this is Fermi case.
Yeah, if you want the bosonic case,
that should be permanent. Yeah. This is anyway. This is everything is written. What you present, this is in archive or some presentation. So I can later ask you in the internet, maybe. Anyway.
Yeah. So this description, there's a separate article. Let me quickly find the archive number here and write it down, because it's with Dan Batea and Anton Nazarov. So it is 2211-13728. It's just a short kind of explanation about this. We're still in the process of writing up the full paper, so that this note here will have the computation that you want, and it's
reference. And then, are there any questions or comments on this talk? I have one question. What is the definition of discrete Hermite kernel in one of your?
So what that is your kernel of, let's say, M and K is Hermite M Hermite K minus 1 Hermite K Hermite M minus 1 over X minus Y. This is X, Y, Y, X, if I remember correctly. And then you take no, sorry, this is M minus K.
Okay.